All right, so we're going to a little transition here from what you did last year in pre-calc to a calculus approach this year. So last year, I'm sure at some point you talked about the PERT equation, right? That's an R, by the way. A is the amount, P is the starting amount, R is the rate, and T is the time. And it applies to a whole bunch of different things, and in fact it applies to exponential growth and sometimes decay, depending on the type of problem you're talking about. We're going to eventually get to this point, but in order to get to this point, we're going to take a calculus approach to it today. And it's going to go something like this. We're actually going to end up deriving the PERT equation. So we're going to start with this problem about bacteria. Most of the problems are not very feel-good. They're usually involving somebody dying or getting hurt or some type of destruction involving radiation and death rates and things like that. I apologize. So first we're growing some bacteria, then we're going to talk about some radiation, and then we're going to do nothing exciting except watch something cool, I think, right? Needs cooling? Yeah. A lot of these problems, like I said, involve death and destruction. So let's start with this bacteria one first. If this were pre-calculus, you would then take the information, plug into the PERT equation, solve for some things, and move on about your merry way. But this is calculus, so we need to take a different approach to this. The number of bacteria in a culture increases from 600 to 1,800 in 2 hours. We'll come back to that later. Assuming that the rate of increase, well, we like that word in calculus, a rate, that's a good word, of increase is directly proportional to the number of bacteria present, find blah, blah, blah. All right, first of all, I'm going to use B for bacteria. And then, of course, T is time. I think we might want a skinny pen today. It's because I'm feeling saucy. dB dt, the rate of bacteria growth over time, and our time here is in hours, is directly proportional to, we have to introduce something called the proportionality constant. You can use whatever you want for it. A common variable is they usually use K for that. I don't know why. Some use alpha, some use K. I'm going to use K. Directly proportional to the number of bacteria present. Well, since I define bacteria as B, we start with that guy. And again, if this were pre-calc, we'd take a different approach to it. Pre-calc, we'd start diving right away into the 600, 1,800, 2 hours thing, calculate the rate, do all this other stuff. We're going to use calculus to get us to that point, so we're actually adding more work to it, but it also brings about an understanding. You're not going to have to do this derivation every single time. I just want to show you where this comes from. All of a sudden, we've got a differential equation, which by now you should know how to solve. Remember, K is a constant, so it's a number. B is a variable. Separate the differentials. You could take the K with the B, but it's standard practice to leave it on the side with the T. What next? Hey, you guys are matching today. Did you plan that?
No.
Oh. And you sit right next to each other.
Yeah.
And I've pointed it out to everyone.
Yeah.
Sorry. Looking if anybody else matches, maybe diffuse. I'm just going to stop talking. Taylor, what do I do next? Taylor, what do I do next? Integrate. What's the integral, Alex, of 1 over b?
1 over negative 1. Is it ln b?
Is it good?
Do you need the absolute value?
We can put them in there if you'd like.
Well, I just don't like doing it or just.
Well, it's a great question. Mathematically, yes. But since we're dealing with bacteria, which it doesn't make any sense to have negative bacteria, we're just going to make it magically go away in a second. What's the integral of k dt? Think carefully before you answer. Sam!
TK.
Or KT.
Or kt. Which one would you prefer?
KTA.
KT you like better?
Yeah.
KT. Sam, KT. K
Oh, plus C.
plus C. Okay. Any problems there? Hot diggity. We'd like to solve for b. So now we do the same thing we did yesterday and use the e raised to the trick. E raised to the natural log of b is equal to e raised to the kt plus c. Notice I made the absolute value bars just disappear because, as I just talked about with Lexi, the bacteria will always be a positive value, so we can just drop the absolute value. What's e to the natural log of b? B. Then we talked about splitting this bad boy yesterday. C e to the kt. If this is confusing, let me clarify. That's the same thing as e to the kt times e to the c. Common practice is people will change the variable and all of a sudden turn this into a d or a c sub 1. It doesn't really matter to me, as long as you understand where that comes from, Brent.
If it's equal to that, how does the C end up in form exactly?
Remember, pretty much whatever we do to a constant c, it doesn't matter. So
Just-
e to the c is the same thing as c.
Just C.
Yeah.
Okay.
Yeah. And that's why I put a c sub 1 to identify or distinguish between the two, but you don't have to. You can just call it c or d or q or whatever you want to call it.
Can you do that with K too?
I'm sorry, what?
Can you do that with K also?
No, because it's attached to the t.
Oh, yes.
Does it matter if you do that? Will you still get the same answer if you don't?
If you don't do what? Change it to the e to the c as c?
If you leave the KT plus C.
Yes, because it's going to be more difficult because now what we're going to do is solve for c. Because we have too many variables there. We've got a k, which is also our r. We've got c as our starting amount, and we've got t as time. So we'd like to have only one variable, and that would be t. So this should look familiar. This b equals c to the, or c e to the kt looks just like p times e to the rt. Where c is our starting amount, p is our starting amount, r is our rate, k is our rate, t is t. So we want to solve for our starting amount. What is our starting amount?
C. Right, no, it's actually 600. Bacteria culture increases from 600.
John?
Should be 600 as our starting, because it increases from 600 to 800.
Right. And there's two approaches to this. We can take a logical approach to that. Okay, it's starting and going from 600 to 1800, therefore our starting amount is 600. Or we can plug 0 in for t and solve it that way. Regardless, our starting amount is going to be 600. So now we simplify this. B is equal to 600 times e to the kt. They won't always give you the starting amount. They might say, we start with a certain amount, and then 2 hours later we have this amount, and 4 hours later we have that amount. So you may have to do a little bit more work there. Eventually we end up with 1,800 whatever, bugs. How long does it take for that to happen? 2 hours. So eventually we have 1,800 bacteria, starting with 600, and it takes 2 hours to have that happen. All right, running out of space here. Let's bring this up here and get 3 equals e to the 2k. Where did the 3 come from? Yeah, divide. I got the e thing to itself. How do I solve that? Take the natural log of both sides. So we had a natural log, we got rid of it doing the e trick, now we're gonna do the natural log to get rid of the e. It seems like we're going in a circle, but that's okay. Is that a big enough, or is everybody okay with that jump? You all know that the natural log of e to the whatever is, okay, good. Divide by 2, k is equal to the natural log of 3 over 2. All right, get out your calculators, I need some help here.
Put my notebook in my chair and point five, because the bars are broken underneath. Point five.
Can somebody confirm that number, 0.549? Okay, store this number. Don't use 0.549. It's not accurate enough. Say again? Okay, if you'd like. Which means that now I have my formula here. Let me clear some of this out here, running out of space. We know that that's good to go. Change some color here, go to red. And so we know that the number of bacteria we have is given by this equation. And we've gotten it down to one variable now. The only variable we have to deal with from this point on is t. And again, I'm putting 0.549 up there as an approximate value. Don't use that for calculations. Use the stored value. You might think it's not going to make a big difference, but in a situation where you have to round to 3 decimal places, it will make a difference. And they are sticklers about that. Part B, number of bacteria done to 4 hours. What do I do now? I put in 4 for T. Go ahead, I'll wait. You also might want to be asking yourself, what should my answer look like? Should it be more than 600, more than 1800, less than 1800, less than 600? Is the is the bacteria increasing? Is it decreasing? Well, it's got the word increase in there, so you can probably figure out. But if you plug and chug and you get an answer like 4, you probably did something wrong. If you get an answer like use the value for k to the store. You did? Yeah. No, 4, because we're at 4 hours. We're doing the extension problem. 5,400?
Yeah.
Yeah, beautiful. Part B, 5,400. What if you get, what?
So if you were to do 8 hours, would it go up 18 times?
Well, there's a real easy way to answer that question. Technology is really cool. Let's suppose in a problem like this, I get 5,400.749. How do you answer that?
Round down.
Full bacteria. You gotta go full score.
Do you round up to a whole bacterium? Do you get rid of part of the bacteria? Or do you just answer as the decimal equivalents?
That's in the last full bacteria.
The last one?
The last full one.
So you take that partial bacteria and just get rid of it?
Just cut it off.
Okay? Yeah?
I think it depends on the question, and since this one you can't really have a partial bacteria in this case.
You
You
can.
go down. Well, I don't know. If it was like people, you definitely couldn't have a partial person.
Yes, you can. It's just illegal in most states.
Like it depends on what they're asking, what the unit is.
Okay, so suppose it's people. Sid, what do you think? If I get an answer at 2.751, people, do you include the 0.751 person? Like some guy with only one leg? Or do you round up or do you round down? Do you go find a quarter of a person and stick it on him, or do you just dispose of 3/4 of that body? Okay. I don't necessarily have an answer for you. I mean, the way I would handle it on the AP test and the way they handle it most of the time is you're better off leaving the decimal answers on there and attaching a note that says, I know you can't have 0.751% or of a body but I left the answer there because again, they're big on 3 decimal places. It makes no sense whatsoever, but better safe than sorry. Okay. In a lot of times on the AP test itself, it'll say to the nearest dead body, how many people, blah, blah, blah. It doesn't have to be a dead body, it could be a person. Or to the nearest bacterium. Is it bacterium? Want to say there's one? You got one of them is bacterium. Answer here. So then a lot of times they'll tell you how to answer, so you don't really have to worry about it. Okay. We good on this one?
Yes, sir. It was
Outstanding.
80, it was 81 times.
It was what?
81 times the original. If you do 8 hours.
Yeah. Okay. Because it's exponential.
Yeah, 390.
Gotcha. All right. Let's look at some radiation stuff. Do you know what Half-Life is?
Yeah.
Other than an awesome video game.
So are you waiting for Half-Life 3 then?
Yeah, I'll be dead before that. Casey, what's Half-Life?
Half-life is the time it takes for a thing to decay and only have half of it.
So where's the other half go?
It radiates away,
It disappears.
I think.
Yeah, you're right. It just breaks down into elements and disperses. So if I start with a chunk of radium, radium has a certain half-life, and in fact, radium's half-life is 1,600 years. Which means that if I start with a 10-pound chunk of radium, in 1,600 years, I'll have a 5-pound chunk of radium. It just goes away. Then in another 1,600 years, I'd have 2.5 pounds of radium. And it just keeps disappearing and disappearing over time. Will it ever disappear?
No.
No, you just keep dividing things in half over and over again. That's why, like, Chernobyl is still uninhabitable, because there's still radiation there after, I think it's been 30-something years, 40-something years. So let's talk about some radium here. It's got a half-life of 1,600 years. Find the amount, Y, remaining of 50 milligrams of pure radium after T years. So let's start this one without deriving. We'll go right to the PERT equation. Okay, where's my, hold on, let me find my notes here. Yeah, we don't need to derive this one. We'll go right to it.
They're not even using T1 half. 0.693, yeah.
There's the true PERT equation. You can adjust it using whatever variables you want. Like, for instance, in the last problem, we used K to be the rate. If you want to use R, that's fine. If you don't like P and you want to change P to R for radium, or change A, I don't care what variables you want to use. It's entirely up to you. The standard in calculus is usually K for rate and C for your starting amount. And Sam has a question.
So the last one we derived to get that, do we always have to do that, or do we just?
Only if the problem tells you.
Okay.
And in fact, I think 11 and 12 tonight on the homework you should derive. The others, you're just going to go to this.
Okay.
Okay.
Is there always like the same steps when you're deriving?
Yes, what changes is the initial equation that you start with. You'll see when we get to the law of cooling, it's a little bit different. So we have a half-life of 1,600 years. What does that mean? Well, one chunk of information they don't tell you in the original problem is, forget about part A. In the original problem, they don't tell you how much radium we start with. So let's suppose that P is 10 pounds. After 1,600 years, what would A be? 5 pounds. Suppose we start with 1 billion pounds of radium. After 1,600 years, how much will I have left? Right, half of 1 billion. So if I start with P amounts of radium, how much will I have over 1,600 after 1,600 years? 1/2 P. And actually, that T should be 1,600. Sorry. How many variables in that equation?
2.
2. Good. Can I make one of them disappear?
Yeah.
Can I divide both sides by P?
Yeah.
Now, the reason I ask that question is because, remember, one of the rules we have is never divide by a variable Unless
You know it's not zero.
you know it's not zero. Can P be zero?
No.
No, because if we don't have any radium, we're talking about something that doesn't exist, so we skip it and move on. So we're sure that P can't be zero. What do you got?
Do you do the natural log?
We're going to. Yeah. Let me divide by P first. So your starting amount initially is irrelevant. Whether I start with 10 pounds or a billion pounds, after 1,600 years, I'm going to have half of that starting amount. Okay, now what'd you say? Natural log?
Yeah.
Okay. Take the natural log of both sides. And again, technically speaking, we should have absolute values around that, but we all know that 1/2 is a positive number, so the absolute value goes away. So R is equal to the natural log of 1/2 divided by 1,600, which is approximately equal to? Are you doing that in your head, Kev? Okay. Don't try too hard, you'll hurt yourself. Whoa. Give me that again.
Negative 4.3.
-4.33. Go one more, 3 decimal places. 2.
2 times e to the negative.
And there's that little e on your calculator. That means times 10 to the
Negative 4.
-4. All right, what does that mean? That means that we're in exponential, sorry, not exponential notation, I said it wrong. Scientific notation, and that's a really tiny number. If you prefer, 1, 2, 3, 4, negative 0.00043332. Don't confuse the e on your calculator with the exponential e, the 2.718281828459045. Store that number. Sam, can you talk about that negative sign there? Why is there a negative sign there?
Because it's decreasing.
Good. Negative sign there because our rate is decreasing. In the previous problem, we're getting more bacteria as time goes on. In this case, we're getting less radium as time goes on, so the number should be negative. Which gets us back to this monster. The amount of radium that we have is our starting amount, which we'll get to in a second, e to the that mess, negative 0.00043332 t. And if we look at part A, we're starting with 50 milligrams of pure radium. Once you get to that point, life is good, because now you can answer all kinds of questions. And there's pretty much only 2 questions to be asked. How much time will it take to have X number of milligrams? Or how many milligrams of radium will you have after X or T amount of time? So we got the formula, part A is taken care of. When will the amount remaining be 20 milligrams? Will the answer be more or less than 1,600?
More.
Well, I got both.
Oh.
I guess we didn't look at the third possibility.
More. Or the same.
Right, or the same. How much radium will we have after 1,600 years? 25 milligrams, because it's half. So therefore, will the answer be more or less? More. Good.
Wait, how do you get that? That is more.
Because after 1,600 years, we'll have 25, because that's a half-life, and therefore,
How do you?
you're told the half-life is 1,600 years.
Oh, okay.
So remember, no matter how much you start with, after 1,600 years, you have half of it.
Oh.
And since the problem says 20,
Oh.
we've got to lose
yeah.
more, so it's going to be more than 1,600. Divide both sides by 50. I get 2/5. E to the negative 0.00043332 t. Natural log. So I'm going to skip a couple steps here and realize that t will be equal to the natural log of 2/5 divided by negative 0.00043332. which is actually that number you stored on your calculator, which gives us a time of approximately, go,
2,115.085 years.
0.0 what?
85.
Can somebody confirm?
Yeah.
Awesome. More than 1,600, we're happy. Cam?
Can these type of problems like fluctuate, like go up and down? Like the rate goes from an increase to a decrease? Okay,
No,
so-
because then it wouldn't follow a true exponential model.
And so they can't ask you what time will it be this or this amount without it being like extremely easy. Like they wouldn't do that.
I don't know if I understand
Like
your
they give
question.
you a quantity and a time, and they're like, what conditions will it be both of these under? You know what I'm saying?
No.
Because if it fluctuates, then it could have been at that point multiple
Then
times.
it's not doable because it doesn't fit the exponential model.
I need it to be.
Okay, any problems? So the first one we saw a derivation of, the second one we went right from the PERT equation. The third one involves a different type of problem because it's a law of cooling. Can I erase this?
Yeah.
So this is really the meltdown problem.
I hadn't really thought of that, but yes.
Meltdown would be like. if
Also,
it's
I
warm.
looked up Chernobyl was 86.
I'm sorry, what?
Chernobyl's 86, so this year will be 32 years.
Oh, okay.
More than 32
That's
years.
when it happened. So sorry. I got over it though. According to Newton's law of cooling, the rate at which an object cools is directly proportional to the difference in temperature. Okay, hold on, let's stop there for a second. Let's start writing some of this stuff down. The rate at which an object cools, how can we express that? Wait, does it tell us in the problem what? Okay, so let's use y as the temp of the object. Temp of object. And the only reason I'm using y is because that's what I used in my notes. T is time.
It sounds like define it. It sounds like monkey. What number are you?
Come on, I bet
Oh, here it
it's
is.
mine. Yeah, it's on
Hello?
Oh dang.
I'll call him back.
That's my phone. I sounded like mine, that's how I know.
You can actually like set the vibration pattern for like different
Like
contexts.
the time do not disturb, so I know it's somebody in my favorites list because I still allow them.
The subscriber you have dialed is not, so it's probably a. They've called you 3 times though. They must really want to get in touch with you.
Who is it?
Should I leave a message?
Yeah, thanks.
No, I
Maybe
just
don't
got a
scare 'em off.
message. Darn it. Yeah, scare them off like they care.
This is Lexi's math teacher.
Don't ever call again! Dude, don't call that number!
That math teacher's.
Cause he's psycho! He showed up at my house!
Well, we all know you care for us then, you know?
No, I don't really. The rate at which an object cools. How would you like to express that rate?
DC.
Why would not just K.
Not K. It's a rate. It's a calculus rate.
DR.
I heard some people say it, so I'll just go with it. dy over dt. The rate at which the object cools over time is directly proportional to. So we need a proportionality constant. What would you like to use for a constant? K?
Yeah.
K.
We could just use kindergarten word as a concept.
Is directly proportional to the difference in the temperature between the object and the surrounding medium. Ooh. What's the surrounding medium? Well, that differs on the problem. Is this thing sitting in water? Is it sitting in air? If I read the problem here, the surrounding air temperature is 75 degrees Fahrenheit. The difference between the temperature of the object and the surrounding medium is expressed how?
Y minus 75.
The absolute value.
Nope. Okay, that's the hard part. We'll come back to the other stuff in a second. That 125 to 100 and all that other fun stuff there.
What's K again?
Proportionality constant, which will eventually become our rate. So, is it safe to assume that you remember this from chemistry about how cooling works? If the temperature between the two objects is more extreme, then the cooling happens faster. If they're closer together, it happens slower.
I don't think we learned that.
You never learned that?
No.
We learned
So
that.
if you put if you put a 500 degree heated up ball bearing into 40 degree water, it'll cool much faster than if you put a 43 degree ball bearing into a 40 degree.
Oh,
Well, really, it's heating the water. But the ball bearing's heating the water.
no.
He's right.
Well, actually, it's heating the water. No such thing as cooling, just like heat.
Yeah, I'll dig up Newton and tell him that. Hey Isaac, you wrong. Whoops.
Do you like that cooling stuff? Nope. That calculus stuff?
And again, I left the K with the T, because the K and the T work well together. Integrate. Think carefully before you answer. What's the integral of 1 over y minus 75? Correct. What would u be? Right. Which strangely enough, then it turns out to be 1, so it is actually what you think it's not supposed to be, which is the natural log of y minus 75. I just wanted to be clear, however, that this is actually supposed to be done as a UDU problem. What about the absolute value? Do I need it here?
No, because the temperature's not gonna be negative.
Second anything?
Temperature's not gonna be negative.
Why can't
Temperature can be negative.
Not at this point.
Hold on. Wait. Can temperature be negative?
No.
Yes.
No, it cannot be.
Can the difference in the temperature be negative?
Yes.
In other words, is there any reason why y can't be negative 2 degrees? I could show something down to negative 2 degrees, right?
But
Can
not
the
study.
difference between the temperatures be negative? In other words, if I take an object that's 125 degrees and I lay it out in a room that's 75 degrees, can that object get colder than the room temperature? No. So therefore, do we need the absolute value?
No.
These are the kind of things that seem trivial, but you want to be thinking about when you're trying to plow your way through these problems. And again, that's a subtle difference. It's not going to cause you to get the whole problem wrong, but it could be the difference between an 8 or a 9 on a free response question. E2 trick. By now this should start becoming a little bit easier. I made a big jump there. Is everybody okay with that jump? Remember, e to the kt plus c can be split into e to the kt times e to the c, and e to the c is the same thing as c. I just put a sub 1 in there so we can tell the difference between the two. Which means that y is equal to c sub 1 e to the kt plus 75.
Do you think we should put a sidebar in there saying C1 is equal to e to the c?
It wouldn't
Just-
hurt.
Yeah, just for the AP.
Yeah. Just so that, I would assume that the person grading it, well, I wouldn't assume that the person grading it has a clue of what you're doing. Okay, general formula, now we need to start solving things. Let's see, what do we know? We know at t equals 0, what's y?
125.
$1.25. We know that when t equals 1/2, y equals, wait, is it, no, oh, it's that because I make it half, yeah. What is this?
100.
Hondo. You know, be aware that this problem is a little bit different because we've got that plus 75 on there. So C1 is not going to automatically be $1.25. It might turn out to be, but we're going to do it the hard way. We know that the temperature is 125 degrees. We don't know what the starting temperature is. When T is equal to 0, so that's e to the 0 plus 75.
I think you do know the starting temperature.
Second anything?
You do know the starting.
But we don't know what C1 is in this problem. Okay. What's e to the 0? 1, so therefore C sub 1 is 50. In the previous problems where we just started with a PERT equation, we knew what our starting amount was. This is a little bit different because we've got that plus 75 hanging around there. So that C sub 1 is not necessarily our starting temperature. I mean, it doesn't make any sense in the problem, but mathematically it works perfectly well. So now we get back to this. I'm going to change some colors here. So y is equal to 50 times e to the kt plus 75. Still have one more variable I need to figure out, and that is the cooling rate. Will my answer be positive or negative? Negative, because it's cooling. Use my second chunk of information. When t equals 1/2, y is equal to a hundo. 100 equals 50 times e to the 1/2 k plus 75. All right, this one you're on your own. Solve for k. Remember your Aunt Sally.
I think we have to solve. Do it. It's time to speak those. Negative 1.3.
Patrick, what do we got for k?
Negative 1.386.
And we've already had that confirmed, so we're good to go. Any problems with that? The reason I said Aunt Sally is because remember you got to move the 75 to the other side before you divide by 50.
Is it for negative 0.1?
No, 1.386. You off by a decimal point?
The final k equals 1.5 divided by half.
Times
No.
2.
It was 1.5 times 2.
Oh, it's 2.
Yeah,
Okay.
because you got to get rid of that.
Um,
Okay, after everything is said and done, we have this final equation. Y is equal to, where am I at? This one. 50 times e to the negative 1.386 t plus 75.
This one's a lot harder.
Yep, because of that minus 75 in there. The law of cooling things are always a little bit trickier. Especially since they don't fit into the standard PERT equation. I've got that formula down to only 2 variables. So again, the same 2 questions I talked about before pop up. How much time does it take for it to reach this temperature? And, what's the opposite of that? What temperature does it have to start, or what temperature is it after a certain amount of time? Okay, we got it? Question, Kev?
So when you plug in T, do you plug in 1 or a half?
For where?
Because it says find the
excellent question. It would be one, right, because we've done a half hour and then another whole half hour. Good? Think you can handle it? Awesome. Tomorrow then, as I said, is our 100-day party. Don't forget your stuff. What are the 2 things you need?
100 things special.
100 things and some type of food or crappy sons or whatever.
What if you're combining them?
I don't want to get involved.
What do you have that you have 100 of?
Oh, I'll bring something, don't you worry.
I think if we counted, you might.
Everything, anything I have that's special, yeah, I don't have 100 of.
Counting out 100 things
I only
takes
have
a
100
long
of
time.
time.
Does anybody?
Okay, well,
I'll find a penny on the ground.
Set myself
No, just
free.
one penny that's 50 years old.
Oh, okay.
They didn't make pennies under your yard.
Oh, it's actually over there.
Press
It's
penny collector
at,
knows more about pennies, Sam.
I'll find it for you.